Okay, so once upon a time, we talked about differential forms, and I told you that this is the differential form right here, this thing that we're integrating. And basically, I just said it was like a notation, and we didn't put too much into it. Okay, turns out that thinking about differential forms actually is the key to unlocking the unifying features of this whole rigmarole. So I'm not going to go into full detail about what a differential form is because it's beyond the scope of the class. But what you should think of it as, it's going to be, there's going to be some function bits, and then there's going to be some dx's and dy's, and those can vary depending on how many dimensions we're in. So the general type of differential form, let's just write it as there's going to be a sum of some terms. Each one has a function for a coefficient out in front, and then there's going to be some dx's and dy's and whatnot. I'll just call it d alpha for short. So this is a general differential form, and we're going to be interested in looking at the operator d. And what does d do to a differential form? So it transforms it, and the way that it does it, so the sum stays the same, but now we replace f with the partial derivative of f with respect, I forgot to include my other summation. I equals 1 to n for however many dimensions we have, and we've got the partial derivative of f with respect to the ith variable, and then we also have dxi attached onto d alpha. And you're probably thinking, what the heck is this wedge right here? It's actually what they call it. They call it a wedge, for lack of anything else. So the idea here is that a differential form is think of it as a field with orientation. So we've seen that orientation is important and orientability is important. And so this is basically just a widget for keeping track of orientation. And so it has a simple rule, and that is that if you have, so instead of looking at just the area element dx dy, we're going to have dx wedge dy. And so that actually incorporates an orientation as thought of by the cross product. So if this is our little dx vector and this is our little dy vector, then the one coming up here, so this is going to be oriented by right hand rule. So if you do the right hand from dx cross dy, you're going to get this one coming up here. That would be dx wedge dy. And this is exactly the same thing that we saw when we were looking at using the magnitude of the cross product of the partial derivatives to find the area of the little parallelogram that needed to be integrated up, right? And so if you do the cross product in the opposite order, you're off by a sign. So the rule is that this is minus dy dx. And then the upshot of this is that if you have dx wedge dx, that's equal to, now I can flip the order of them and get minus dx wedge dx. So it's equal to its own negative, and the only thing that that's true for is 0. Okay, so these two little rules that you can flip the sign and that the double with the same variable is 0, those will be useful. Okay, so now let's go back to this godforsaken mess of a formula and see what it means. And you'll see it's not so bad at all once we look at an example. So the most basic kind of differential form is just a function. So here's f. F is what we would call a zero form because it has no dx's or dy's or anything attached to it yet. Okay, so then we take d of f. So we apply the differential operator d, and we get df dx. So what does it say to do? So just going back here, it says, okay, we're going to take the sum of partial derivatives and now tacked on with a d corresponding to whatever we're differentiating by. So I take partial derivative with respect to x and tack on a dx. And I take a partial derivative with respect to y and I tack on a dy. And I take a partial derivative with respect to z and I tack on a dz. And then because this says I need to sum from I equals 1 to 3, I'm going to add these up. Boom, boom. Okay, and then you look at this and go, oh, good God. I know that face. I've seen it before. This guy right here, this is exactly df, the differential, from section 14.4, right? Back when we were looking at tangent planes and approximations, the notation might have been slightly different, might have been actually exactly the same, but that's exactly what it is. And then at some point when we were looking at chain rule and other things, we saw that this is actually the same thing as the gradient of f dotted with dc, right? Okay, so this is, we just looked at how d acts on a zero form, aka just a function, a scalar function. Okay, so now let's look at what happens, how d acts on a one form. So a general one form is going to have some dx term and some dy term and some dz term. So this here, this is what a one form looks like in R3. Okay, and so again, we're going to say, what happens when we take d of this thing? So we apply d to this one form, and what do we get? Well, the godforsaken formula says we first have to do the derivative with respect to x and tack on a dx to each term. All right, so we can do that. So let's see. So we're going to have partial of p with respect to x, dx wedge dx, and then we're going to have partial of q with respect to x, dx wedge dy, and then we're going to have partial of r with respect to x, dx wedge dz. So this x, y, z, that's what there was originally, and then this dx, 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 that's what I just tacked on. That's the new addition coming from right here. Okay, that was the x term of this sum, but we also have to do it for the other variables. So let's go and figure out, okay, so we've got this guy. Now we also have to do the dy derivatives. So just to show you how similar this is, I'm going to copy and paste and say, okay, so now we take out the x derivatives and we take out the dx wedges, and this becomes y dy, y dy, y dy. And of course we do it all again for the last term, where we've got z, partial z dz, partial z dz. Okay, then we go back to these rules over here to simplify. So first off, any repeats are dead. All right, so we can kill off this guy and this guy and this guy. Okay, and then we can collect some common terms, because over here we've got dy wedge dx, and that's minus dx wedge dy, and dz wedge dy, so that's minus dy wedge dz. And up here we have dx wedge dz, which is minus dz wedge dx. And you might say, hey, why are you doing that one and not fixing this one so that it's in alphabetical order? And the answer is because math don't care about alphabetical order. What math cares about is orientation. And so if we have dx and dz right here, then if you take the cross product of these using right hand rule, and you want this one to come out, that's going to be dz wedge dx, not dx wedge dz. Okay, so let's see. So we can group now, and we have so for our first term we'll have the one. This is the x component, and dy wedge dz is what's going in the x direction. So we have ry minus qz right here. So we're going to have ry minus qz dy wedge dz. So that's going in the x direction. And then we're going to need the thing that's going in the y direction. So that's going to be the coefficient of, dx wedge dz. And so we've got one here and one here. And so that gives us pz minus rx. And then let's see what else we've got. We've got the x wedge dy part that's going in the z direction. And so where are those guys? Those guys are, oops, lost my tool here. Dx dy and dx dy. Okay, so we get our q dx and our p dy. Okay, and stare at that for a moment and you realize, oh, look at that. That's actually the curl of a vector space, or vector field dotted with d sigma. Okay, so the way that that the differential form acts on a vector field is it takes it to the curl. All right, and then let's look at a general 2 form and see what it does. So for a 2 form, we're going to have there'll be the x component p dy wedge dz, and then the y component, which will be dz wedge dx, and then the z component, which will be dx wedge dy. Okay, so this guy here is in general what a 2 form looks like. And we apply D using the same crackpot formula. So let's see. So when we do the first term in the terrible sum is the x derivative. So we're going to have px and then dx wedge dy wedge dz, and then qx dx wedge dz wedge dx, and then we're going to have rx dx wedge dx wedge dy. Okay, and so that's the first thing in our summation that we get from doing ddx. And then we're going to have the stuff that we get from doing dy. But before I do all of that, I want to point something out. And that is there's a lot of things dying off here. So for instance, here we have dx wedge dx. And so I can interchange these two and change sign, and we get the same thing that we had before. So it has to be 0. Bam! So that thing is 0. Over here, I can interchange these two, picking up a sign, and then it would look like dz wedge dx wedge dx. And then when I interchange these two, I pick up a sign and have the same thing. So that one also dies off. Ooh! So things just got much simpler. So the only one that survives in the second round is qy, and then we have dy wedge dz wedge dx. And then the only thing that survives in the third round is going to be rz dz wedge dx wedge dy. And now let's see what happens. Well, I can interchange these two, and it will look like it'll look like minus dx wedge dz wedge dy. And then I can interchange these two, and I'll get add another minus sign, so that cancels out the original minus sign, and I have dx wedge dy wedge dz, which matches with this guy. Similarly, if I interchange these two, I get that, and I pick up a minus sign. And then if I interchange these two, then I'm back to dx, dy, dz. So what do I get here? I get px plus qy plus rz dx, dy, dz. And lo and behold, if that isn't the divergence of a vector field dotted with the oriented volume form, dv. Okay, so maybe that's silly to call it a dot product because we're actually just looking at vectors of length 1 here. So most of the time we would just write it as div f dv. But now look at what has been going on with d. This thing that we ended up with here at the end, this is a 3 form. So d took us from a 2 form to a 3 form. And before that, we had that the output that we got here. This was a 2 form. So D took us from a 1 form to a 2 form. And back in the very beginning, we had that D took us from a 0 form to what is clearly a 1 form. And this all works in general in higher dimensions as well. It turns out that you can't have, so by this rule right here, you can't have 4 forms in R3. They just die. Everything goes to 0.